when we're designing networks, it's really important to think about where we are now, where we're going to be in 3 years, and where we're going to be in 5 years or 7 years. And to that end, many hardware manufacturers are using licensing models that kind of follow that prescription. So said a different way, a lot of the hardware vendors are actually introducing this concept of leasing licensing for some period of time. And the idea is that we want to make more efficient the management of operating system licensing and simplify the process that you all as network administrators have. So when we talk about network design and we talk about the desired attributes that we actually want to achieve, scalability is among the one of the most important attributes. Scalability really accounts for growth. Where we are now, if our network continues to grow, we will obviously be somewhere different in 3 years or a year or 5 years or some arbitrary length of time. So when we think about scalability, we also need to think about what kind of new applications are going to actually be flowing across our networks. So for example, in the olden days of network design, many of our devices were what are called fixed chassis, meaning that whatever device, switch, router, firewall, any kind of an appliance that you pulled out of the box, that chassis was fixed. In other words, it was not changeable to increase the speed of the interfaces or anything like that. In today's environment, although you can still acquire fixed chassis appliances, the more popular option is to use what is called modular chassis appliances. So as an example, at the access layer, and I'll just kind of focus in on that a little bit, at the access layer, we want to have some degree of modularity so that as we connect additional users into our access layer devices, we can then aggregate that with higher speed uplinks into our distribution layer. Another attribute that we want to talk about with regard to desired attributes is we want to talk about resiliency. So resiliency has to do with very high reliability and very high availability. So you'll notice here that in this particular network design, when we start to aggregate our traffic flows from the access layer up to the distribution layer actually uses multiple links within this combination of distribution layer switches. And it's also worth offering that this is also where a lot of our policy, a lot of our access control, a lot of our services are going to actually reside. So things like wireless LAN controllers, egress points out to the internet, egress points out to other remote site locations, a lot of that is going to take place in the distribution layer. Security is another concern that we need to look at when we're talking about network design. And so relative to security, there are two key components that we need to focus on, one of which is physical security. If you've ever looked at the back of an enterprise network switch, one of the things that you'll probably notice is that it has a small slot that is carved out of the actual appliance itself, which is for a locking mechanism. So there are instances where we may need to physically secure the hardware appliance in the rack, in the room, or in the, wherever the appliance happens to be. You might have heard of those that are sometimes referred to as Kensington locks. And so those actually physically secure the appliance so that the appliance cannot be stolen. In terms of services security, that really relates to things like being able to implement port security, access control lists, usernames and passwords for local authentication into the device. So that's another attribute that we want to think about when we're designing our network. And finally, we want to talk about quality of service. And quality of service is important because in this particular network architecture, probably at this layer up here, when we're communicating with our various servers, we want to be able to differentiate traffic flows. So if one of these happens to be our voice call or our voice controller, our UCS appliance, we would want to be able to differentiate traffic flows through the distribution network and into the access layer network so that our voice quality doesn't drop when we have congested interfaces. As it relates to two-tier, a lot of this is going to be based on the size of the network. There are lots of design guides out there in the on the internet, and various equipment manufacturers produce design guidelines for our network architectures. And so where we really start with design is this idea of saying, how large is the network? How many users are we supporting? How many endpoints are we supporting? And you know, to what degree do we need to manage the traffic flows for those users? So the general guidance as it relates to two-tier versus three-tier and any modularization that takes place in those would be, first of all, to start with the size of the network and also the applications that are actually running across the network. So the ratio of real-time versus non-real-time traffic flows. So for example, you know, TCP-oriented web requests out to the internet behave very differently and have very different latency requirements as compared to voice traffic, which has a very low latency requirement end-to-end from IP phone to IP phone. However, regardless of whether it's a two-tier design or a three-tier design, we need to keep in mind that, first of all, cost is going to be involved as a decision point for how we architect the network, and also, are we going to what degree are we going to provide redundancy and load balancing? So when we get a little bit deeper into this and we start to talk about spine leaf architectures, that's a very different model as compared to a traditional two or three-tier network design. Now, the current guidance from Cisco suggests that when you have a small network, which means up to a couple of hundred devices or 200 devices, that a two-tier design, or actually a single-tier design with a single egress point, so in a small network, it would look something like this. So in a small branch network, you would have some kind of an access device that you would then attach endpoints to, or wireless access points, or whatever the case might be, and an egress point out across the WAN, going back into some central network location, usually a headquarters location or something like that. The access layer, however, provides user access into the network. And so what it's really designed to do is it's really designed to be that first hop into the network architecture. It's also designed to be where users get classified and designated in terms of VLANs and things like that. The distribution layer, which is kind of up here, this is our distribution layer. Our distribution layer is an aggregation layer. So the distribution layer, and you'll notice that the amount of redundancy actually changed from the access layer here to the distribution layer, where we start to have multiple links. And the whole idea here, again, goes back to resiliency. If I have a link loss, or if I have a physical failure in between this distribution switch and this distribution switch, let me just kind of point those out a little bit. If I have a link loss right here, then I still have resiliency in the form of that second link. And if both of those links die, then I can still get up to my server architectures at the top of this network successfully. What's often said about the access layer is that this should be switched access. Now, where we start to differentiate that is when we start to talk about software-defined networking, which is something we're going to kind of visit later on in the presentation. This is said to be switched or layer 2 access. And what that means is that here, these devices are going to make decisions on where to send traffic flow based on layer 2 information. The distribution layer, however, is said to be routed. And what that means is that things like access control lists and other control mechanisms that I put in place, VLANs, and all of the other ways that I differentiate traffic flows in the network all kind of go into the distribution layer. So this is said to be kind of a routed environment. And then if I have, in the example of a 3-tier design, what I now have is, especially if I have multiple distribution layers in a campus environment, as an example, that is said to then go into a core layer. Now, I want to point out here that these diagrams show this modularity between access layer, distribution layer, and core layer. Now, the core layer again goes back to high-speed switching between different distribution layers. So where you might see a 3-tier design, or what's sometimes called a collapsed core design, where I actually implement core layer functionality, and I'll just kind of draw a quick picture of that. So where I actually collapse the core into the distribution layer, which is usually a factor of cost and of benefit of getting the most out of my network equipment, that I might actually have what's called a collapsed core design. So usually blade type switch architectures are used in that kind of a design. In any event, a 3-tier design is typically going to be for your larger network, so greater than 1,000 devices, and with a great deal of with a need to greatly control the interconnections between the distribution layer, the various access layers, and of course the core layer. What is also usually involved in having a core layer device is it actually reduces the number of physical connections required between different distribution layers that are making up a campus. Modularity comes into play when we start to consider within our design how we want to prevent large failure domains. And so modularity gets involved here because if we have a scenario where, for example, we have a data center. So in our data center, this is where we're performing a lot of our, or this is where we're providing a lot of our services, our applications. And so we have sort of this enterprise campus. So this enterprise campus right here is going to provide all of the functions required for our end user connections, for our also for our remote locations kind of out here. So it said a different way, modularity gets involved when we start to modularize the network, and we modularize the network so that if we have some failure within some portion of the campus, it doesn't have a far-reaching impact out to the balance of the user communities that are in different modules. You might also hear it referred to as a services block. And so a services block would an example be our data center that kind of comes up off of the enterprise campus, or maybe even off of the edge distribution. But the whole idea here is to allow for the eliminating the failure of one domain from having a far-reaching impact into the balance of the domain. It also greatly reduces the management complexities when it comes to identifying problems and solving problems within the network. And so they've kind of given these things names, right? So the management block, for lack of a better thing to call it, that's where things like my SNMP traps and my syslog messaging, my DHCP management, my management of the network infrastructure or architecture that makes up my network. That's where a lot of that's going to take place. This is also typically where I'm managing things like firewalls and management platforms related to my data center. The enterprise campus is exactly that. It's where users connect up, have access to the network. So the enterprise campus can actually be multiple access layer devices going to a central distribution. The edge distribution portion of my network is where I'm going to aggregate all of my access layer modules into a distribution layer, and then that goes out to the enterprise edge. So you can think of the enterprise edge as the edge of the enterprise. So if I were to draw kind of a square around all of this, it would look like this. So it would kind of look like this would basically be my network architecture right here. And then also within this, I might also have a data center. I might have other services going on inside of here. In this modularity, though, this modularity gives me the ability to more easily manage the different users and different user communities that I have out here. This is also where I would have a VLAN to IP architecture marriage. It would be where I would typically have my firewalls. I'm going to typically have a firewall here so that I'm monitoring all of the traffic flows leaving and entering the enterprise. And then that usually marries up to a service provider edge of some kind. And this I usually don't have any kind of control over. This is usually a subscribed service that I'm purchasing from some service provider. So this can be anything from MPLS to other types of, ATM, frame relay if I'm using serialized interfaces on my edge devices. And usually this is usually based on some kind of a service level agreement that basically guarantees a certain number of packets per second and a size of packets per second. And then, of course, over here in my remote section, this might be for any remote office locations that I'm also managing. So, in effect, modularization is not required. However, the larger the network becomes, the more important modularization becomes, because again, the more efficiently and systematically I want to manage the network. Spine and leaf architectures, which are typically found in the data center, really introduce this concept of very highly redundant links. So down here on my servers architecture, I'm going to have things like application servers and DHCP and, so things like your SharePoint and your email servers, Exchange, all the different server architectures that I'm using. And so in order to get the most out of those servers and in order to provide the most efficient use of all of those servers, and by the way, we'll talk about this here coming up, but most of these servers are actually going to be virtual machines. We will have effectively these what are called leaf devices. These are typically high-speed switching that are also connected up to a spine. And so the advantage of leaf spine is that unlike traditional switched access, these are typically going to be point-to-point layer 3 links. So they're going to have IP addressing architecture associated with them. The whole idea here is that as traffic flows, we can use different things like, for example, equal cost multipath is a typical use case example in our data center where we're equalizing the cost of the traffic flows going over to our servers so that we get the most efficient use out of this. Another attribute of spine leaf network design is that there are no broadcasts in here. So this is all unicast traffic, and so we actually eliminate the overhead related to broadcast traffic by simply making all of this unicast traffic. The other thing is that because of equal cost multipath and some other attributes, we basically eliminate a bottleneck. Anywhere you have a bottleneck, in other words, anywhere in your network that is actually smaller and less efficient and less capable of actually carrying the flow of traffic that the network is currently demanding, we get rid of all that. The other huge advantage to this design is its elasticity. So by elasticity, what I mean is this ability to actually add more leaf devices as the network grows or as the demands require, and simply connect those up to spine switches and on a very rapid basis be able to increase the capability across this two-tier design relative to getting traffic in and out of server architectures. So it also increases the bandwidth. So all of this is kind of related to the things that we want to design. Now, again, typically, spine leaf architectures are going to be found in data center environments. They're not typically found in the traditional network environment that you might have at your office or your company or on your campus or whatever the case might be, but it's almost certainly going to be found in your data center. The other thing about spine leaf is there are specific operating systems and specific architectures of equipment that typically are found in spine leaf designs. The Nexus family of operating systems and the Nexus family of equipment will typically be found in a data center environment.